Good. So we finished the dropout regularization technique. It's really something that you heavily use in training neural networks. Yeah. So and you'll see in the assignment that we do this. So in the next assignment, you will be able to use dropout as a learning technique. Now, there's another technique for regularization called early stopping. We've seen this to some extent when we talked about perceptron very early on. Yeah. So you terminate while validation set performance is better. So what you do is you draw the learning curve. You see the training loss. So basically, the training set loss. That's the blue one. Okay, and then the green one is the validation set loss. And you do what? You train for number of epochs. So you pass over the training data, you run gradient descent for a number of iterations, and then you plot this curve. And look at what is the play. So what happens is in neural networks, because they tend to overfit, because you have a lot of parameters, the error will keep decreasing. The loss will keep decreasing. So you get almost a zero error if you run for a number of epochs. So if you keep training, the more you keep training, the more the error will decrease. The training error will decrease. Yeah, but I can't rely on the training error. So I'm going to look at the validation error and look at the area where the validation loss is smallest and return the weights corresponding to this validation loss. So you keep track of all the weights as you're training, for the different number of epochs, and you just return the weights that return the smallest validation loss rather than the smallest training error. If you use the training error, then you're gonna return the weights here, which are not the best when it comes to validation loss. This would happen to be the best. Okay, so this is called early stopping. It's a very common technique as well in training neural networks. So typically, what I would do in a project is I would use dropout and also use this early stopping technique. Yes. Questions? No? Okay. Now, practical aspects is when it comes to training neural networks, data pre-processing and weight initialization. So we usually do data normalization when we're doing machine learning in general, but particularly for neural networks. For neural networks, it's very important to do data normalization. So if the features have different scales, this means that you have one feature is from let's say 0 to 1, another feature is from 100 to 1000, then this causes a lot of problems when training a neural network, This means that the gradient descent might have to set some weights very high and some very low, because it wanna match the scale of the feature. So this causes a lot of issues. It can drastically slow down learning. So it causes the learning to be very slow. To get a good error or good loss, you will have to really train for a very long time to get to the right scale of weights, because you start with the weights randomly. Yeah, so you start them randomly, so they're usually small values, and then to increase one weight a lot so that it matches the scale of the feature, or make it very small to match the scale of the feature, this becomes it takes a lot of time. Yeah. So ideally, we want to make all the features comparable by normalizing them. Yeah, by subtracting the mean and dividing by the value. What do I mean by this? Here's the original data. So on this graph on the left. Now, what I do is I first center the data, so 0 center the data by subtracting the mean. So I take the mean of every training example. So I compute the mean of every training example where I have, the mean is 1 over n, summation from n equal 1 to n of xn, So xn is a training example and n is the number of example. Upper n is the number of examples. So take the examples and average them. Yeah, so it's a vector. Yeah, a vector of the features. You average these n vectors, you get some mean. Yeah, so some mean of the training data. Then you compute the variance, which is sigma square, which is the difference between the training example and the mean square, and you average this. Similar to any mean and variance, right, in general. Right? You can do this in Excel. Okay, and now you take every training example and you subtract the mean and divide by the variance. That would normalize the data, so make it 0 center and between, right, 0 and 1. So normalized, yeah? So between 0 and 1. Okay?
How do you make it 0 centered?
How do you make it 0 centered? By subtracting the mean. If you subtract the mean, you get it to be 0 centered.
Oh, okay.
And then by dividing by the variance, you make it normalized between 0 and 1. Okay?
Sir?
Yes.
When we normalize, should we, so after training, we normalize the training data and we train the model. So when we want to test it or use it, should we do anything to the data, the input data?
Yeah, you normalize it as well.
Okay, so it should be the same form.
Yes, yes. Use the mean and the standard deviation of the training data to do that, to do the normalization. Okay?
Also of the training data, not the testing.
Yeah, of the training data, exactly.
Okay.
Yeah, but it's very important that you do normalization. So before you train for a neural network, before, and in general for any machine learning model, yeah, you should really normalize the data. It helps a lot with the the training time. Okay.
So, but what if the data doesn't need normalization, like not in neural networks, another model? Should you always normalize?
Yeah, you should typically normalize. It's really a good practice to normalize the data before, to make the features comparable, so that not one feature doesn't dominate the data set because of its scale. Yeah.
Yes, so didn't we use normalization before because the data wasn't linearly separable?
No, we did not. When the data was not linearly separable, we used nonlinear transformations. That's different.
Ah, transformation. Okay. Yeah. Sorry.
Other
yes,
question?
I messed up.
Yeah, that's all right. Okay. Weight initialization. So remember the gradient descent works by initializing the weights, at some values, and then updating them using the gradient. So should we set how should we set the weights? Yeah. So this is a very important question when it comes to neural networks. So we get this as an interview question a lot as well. So what happens when we set the weights to 0? We did this in perceptron. So we set the weights to 0 and it worked fine, perfectly fine. Can we do the same in neural networks? Can we set the weights to 0? What do you think?
I think it will saturate it.
Yeah?
I think we will saturate it a lot. So
I don't think they should be the same value.
Yes, exactly. This is how spot on, right? So the problem is by setting them all to 0, you have the same values, right? You have the same values for all the weights here. What happens here? The signal is the same. The signal is the same. So it's all zeros, right? So the signals become here the same. Signals become here the same. Pass it through the same activation because all of them are using the same activation, ReLU or TAN8. You get the same activations. Multiplied by 0 weights, you get the same signal here, pass it through some activation, you get the same activation multiplied by zeros. So you end up with the neural network, basically all the neurons effectively the same all the time. Yeah. So in the first forward pass, all the signals will be 0, right? Because you're multiplying 0 by the feature values, that's equal to 0. So all the signals here would be 0, all the signals here would be 0, all the signal here would be 0, and so all the activations will be the same. And then you get in the back propagation, so in the backward path, you get the same gradients. So all of them have the same gradients exactly, yeah, because they're all the same weights. And so you get the same updates. So the weights get updated. So everything, all the weights will stay the same. Yeah. So basically, the whole neural network could have single weight, and that's really not effective at all. You don't learn anything from the neural network by having them, all the edges have the same weight. Yeah, so you should really avoid having them the same values. Yeah, particularly 0. I mean, not particularly zeros. If they are the same values, then you're not doing anything. You're not learning anything. Yeah, So, but I mean, why we looked at the example of 0? Because we did this with perception. So it might be one way, an intuitive way to think of setting the weights. Yeah? But you shouldn't really set the weight to the same value. Okay? Good. Okay. So when we talk about initializing the weights, there is a problem called exploding and vanishing gradients. Again, this is something that comes a lot in interviews. So this is how we were updating the weights. We're using the gradient or the deltas, and we would back propagating the deltas from the previous layers. Okay. So as gradients are back propagated through the network, they might explode or vanish. What do I mean, right? I have a gradient here at this layer, right? So delta J of L. For every neuron, there is a delta J. Now, these gets multiplied by the weight, and theta dash of the signal, right? So theta dash of the signal, the derivative of the signal, and summed over all the edges that the neuron feeds on. Okay, so that causes things to either explode or vanish. Yeah, exploding gradients mean the weights of the very first layer. By the time I pass these deltas through the neurons, and multiply by weights and etc. and sum, by the time I reach the very early, layer, either these gradients become very small, so almost 0, or very high. Yeah, depending on the weights and depending on the values of the delta. So they either explode, so they become very large. Yeah, and you update the weights very high. So every time you update the weight, for a single weight, you go from one value to a very high value, or you almost not update the weight at all. Yeah, so that's the vanishing gradient. The vanishing gradient means you almost do not update the weights at all, because the weights depend on, the updates of the weight depends on these deltas. So, okay? Or yeah, you explode them. You become very fluctuating. You update them very high. Yeah, so from one iteration to the other, you're doing really crazy updates of the weight. Most of them are problematic. Yeah, so I want to update the weights, but I don't want them to fluctuate a lot. Okay, so that's the problem of exploding and vanishing grade. So typically, right, as a rule of thumb or practice, coming from practice, you set the weights to a random value, and it's usually in the range from 0 to square root of 2 over dl of -1, or dl of -1, the dimension of the thing. Yeah, so this is just a rule of thumb. Yeah, something coming from practice. But you want to set them to random values. You want to set them to random values, and depending on the, the depth of the layer. Yeah, so this is something that you want to do. Okay, so this is something you have to do also in the training. So when you're training a neural network and you're using a library, you might want to say, how do I initialize the weights? You said, how do I initialize the weights? And you set it typically as follows: as random between 0 and square root of 2 over dl -1. Okay? Questions? All right. We're going to talk about optimization algorithms other than gradient descent, and final thing is hyperparameter tube, so that you can do the assignment on Sunday. Once you do the assignments, everything would become very clear. So once you do, you get your hands dirty with this, really everything that we've talked about will become very clear, because the libraries are very reflective of this. Okay, so the typical algorithm that we use for training neural networks is called mini batch gradient descent. It's not stochastic gradient descent, which looks at a single example, and it's not batch gradient descent, which looks at the whole training set. It's what is called mini batch gradient descent, which is a sweet spot between stochastic and batch gradient descent. So what do? You divide your data set into smaller batches of size m each. So you take your training set and you divide it into batches. Yeah, let's say of batches of 24 or batches of 512, depending on how big your data set is. Yeah, so you look at batches of the training exam. Then you run batch gradient descent on each mini batch. So you really do gradient descent on the whole mini batch. So you update the weights based on the error over all the examples in the mini batch. Yeah, in the stochastic gradient descent, you would looking at a single example. In the batch gradient descent, you would looking at the whole data set. Here you're looking at a mini batch. Okay. And then each complete run on the entire data set, so once you finish all the batches, becomes an epoch. Converges much faster than the stochastic one because you're not looking at a single example, so you don't have this exact issue, right? Or you're very slow because you're looking at one single example, but it avoids local minima and flat regions, which is the advantage of stochastic gradient descent, because you're not looking at the whole global error function, you're looking at it with respect to a single mini batch. Okay, so it has the advantage of both. Okay, you typically set the size of the mini batch, which is the hyperparameter, as a power of 2, and such that the whole mini batch can fit in memory. That's a hyperparameter you need to set when training neural networks. So in the assignment,
wouldn't this take much time?
What's that?
Wouldn't this take more time than stochastic?
Stochastic takes more time. Stochastic, because it's looking at a single example, right? So to get a good error, it's very slow. It's going really, because it will fluctuate. Yeah, it will go, it might, it optimizes on a single example. It will be slower than batch gradient descent for sure, but it's more, it's not heavily, like computationally heavy as batch gradient descent, and it also avoids local minima and flat regions. Okay.
How does it avoid the local minima and flat region?
Because remember, it's stochastic gradient descent, right? In the batch gradient descent, it's looking at the whole error function. So I'm minimizing with respect to the whole error function. So I might get stuck into a local minimum because I'm looking at the global error function, right? With stochastic gradient descent or mini batch gradient descent, I have some stochastic, some probabilistic aspect, some randomization. So I might get out of the local minima or batch or flat region.
Because we're dividing into different batches, small batches.
Right. Yes, because of the randomization in stochastic gradient descent, as Rashad is saying. Yeah?
Okay. Yes, thank you, sir.
You're welcome. Important thing when training neural networks is to use vectorizations and normalize the inputs in each layer over the mini batch. Yeah, so you're doing normalization that we talked about before over the mini batch. Yeah, so not over the whole training set, over the mini batch that you're currently training on. Okay, and use vectorization, meaning what? Meaning that you set everything as a vector. Yeah, so have things as matrices and vectors over the mini batch to make the training quick. Yeah, because Python has really is very powerful when it comes to vector operations. Okay. Now we're gonna.
So what do you mean vectorization?
What do I mean by vectorization? You put things in vector form. So you don't really you put the mini batches in a matrix and you do vector operations when you're doing gradient descent. So that it's fast.
Oh, okay. Thank you.
Don't do loops. Don't do loops over the mini batch. Yeah, I put it in a vector form.
Okay, thank you.
Okay. So this is a variation of the gradient descent. So in gradient descent, we make an independent decision based on the current gradient. So I look at the current gradient and I set the value of the update, right? So I update the weights based on the gradient. So what is the value of the gradient? So this can cause a lot of fluctuation. Let's assume the smiley face is the minimum of the loss function. And this is the current weights, right? So every time I update the weight, I look at the gradient. Yeah, and so this can let me do these fluctuations. Yeah, so because I'm not looking at, I'm deciding, I'm doing local decisions based on the current gradient to update the weights. Now instead, I can take into consideration past gradients to smooth the descent towards the minimum. Yeah, so basically, I assume that you're throwing a ball and you towards like a hole, yeah, or a head. Yeah, you want to smooth the whole, you don't want the ball to jump a lot, right? To go up and down, up and down, up and down. That's what happens with gradient descent. Yeah, we're just looking at local, doing a local decision. Now with gradient descent with momentum, I look at the overall direction. What is the overall direction of the gradient from previous iterations? Is it going in this direction or is it going in opposite direction? So you're smoothing the direction or the gradient based on previous computation. So this is what happens. Yeah, this is the gradient. So delta J of L of t plus 1. That's the the new iteration. And I said instead of updating the weights based on this gradient, I'll update it based on what was the gradient in the previous iteration, right? Combined with the current gradient. Okay, so basically I update the weights based on this Vj of L. So the weights, the new weight is the old weight. Oops. Hi.